Hi, my name is Emily Speakman, and thank you for coming to listen to my talk today on gaining or losing perspective for piecewise-linear underestimators of convex univariate functions. This is joint work with John Lee and Luze from the University of Michigan and Daphne Skipper from the US Naval Academy. So we're going to start by talking about a little bit of background. As I'm sure you know, convex relaxation methods are very common in global optimization, mixed integer nonlinear optimization, linear integer linear optimization, and combinatorial optimization. So the idea is we quite often have a difficult polytope P, so it might be difficult because it's non-convex, for example. So instead, we use a simpler polytope Q, such that P is a subset of Q, to model P, and we often say that Q is a relaxation of P. So it might be that we want to compare Q and P. We want to compare alternative Qs, alternative relaxations. And in the world of linear objective functions, we might consider the average or the worst case objective gap and use this to compare P or Q. But for considering all nonlinear objective functions, we're instead going to compare the d-dimensional volumes of P and Q. This isn't the only way we could compare relaxations, but it is the way we're going to do today. We're going to use today. So the so-called perspective reformulation is commonly used when we have a problem with indicator variables. So for example, here, my z is an indicator variable, and this is a binary variable in 0, 1. So what this does is when z is equal 0, what it does is it forces my x to also be 0. When z is equal to 1, it forces my x to be in this convex interval, so be between L and U. Then usually this is useful because we have some function of x. Usually we think about this as a cost function. And we are trying to model this in an objective function. So by introducing this y greater than or equal to f of x, we can model this using the minimization pressure of an objective function. So here, we've just looked at a scalar z. We can also do this when we have a vector of indicator variables, and we're trying to force our decision variables to some point. When it's off and when it's on, we want to force our decision variables to be in some convex set. So we're going to stick to the scalar case, and there are many applications. So like I said, we usually have some kind of cost function, f of x. We think about this cost function, f of 0 being 0. So if we do nothing, we pay nothing. And then we have a convex cost, usually an increasing convex cost on L and U. So common examples would be a power function with our power p being greater than 1, or an exponential e to the x minus 1. So a very common application is when our power function is in fact just a quadratic function. And this has been studied in this 2010 paper and this 2006 paper in particular. So the perspective reformulation for these types of problems with indicator variables leads to very strong conic programming relaxations. Unfortunately, not all solvers are equipped to handle these. So for example, when our p is equal to 2, we just have this quadratic function. We use the perspective reformulation and we end up with a very nice second order cone. The problem is, if you're using a conic solver, like this is fantastic. If you're not using a specific conic solver, it might be that your solver can't recognize this as a cone, and that can lead to problems. So an main interest of ours is saying, well, there are relaxations that aren't conic, and when would these simpler relaxations be adequate? So if I compare these to the conic relaxations, can I get a sense of how much worse they are? And like I said, we're going to use volume to compare these relaxations. So I have my x, and I want my x to either be forced to be 0 or to be in this interval. I have my cost function, f of x, that it's convex, positive, and increasing. And when x is 0, my f of x is 0. Then I'm going to define this disjunctive set to be the union of the origin with this set I have here. So what is this? Well, my origin, I can think about this is what happens when my binary variable is equal to 0. My x has to be 0, which means my y is 0. This set is what happens when my binary variable is equal to 1. And in this case, my x is going to be between u and L. My y is going to be greater than or equal to f of x. And then I'm also going to bound my y from above. And actually, this picture is going to explain this much easier than I could in words. So I have this origin point here. And then in the z equals 1 plane, I have the curve y equals f of x between L and u. But really my set is saying y is greater than or equal to f of x. So I can have anything up here. The problem is I want to compute volume. And if I have an unbounded set, computing the volume doesn't make very much sense. So I'm just going to introduce this, what I call a lid on y, a very natural lid, essentially the convex hull of this curve, the curve of this graph. So what this disjunctive set is that piece in the z equals 1 plane with the origin. The perspective relaxation of that disjunctive set we get by first relaxing our z to be between 0 and 1. And then in addition, we apply a perspective transformation to our functions that bound y. So this f of x has become the perspective z times f of x over z. And then this lid, we've just taken the perspective of this lid. Now, this perspective relaxation, in fact, gives us the convex hull. Excuse me. So it gives us the convex hull of this piece in the z equals 1 plane with the origin. So we have to just be a little bit careful because, of course, we're taking the perspective here. So we don't want z to be actually equal to 0. So then we have to take the convex closure. But that's really just a technicality. So the perspective reformulation gives us the convex hull. But we can also define a much simpler relaxation. And this we call the naive relaxation. So here, I'm not going to be taking the perspective of any of these functions. They stay the same. And all I'm doing is relaxing my z now to be between 0 and 1. And this is going to give us another relaxation of this disjunctive set, another convex relaxation, but it's not going to give us the convex hull. It's going to give us something larger. So where are we going with this? Well, if you're interested in a little more background, these first couple of papers talk more about where these ideas of comparing polyhedral relaxations for optimization come from. Of course, you may have noticed what we're looking at here is not in fact polyhedral. So in this paper, Gaining or Losing Perspective, it will be appearing in JOGO soon. Here we look at computing the volume of those two relaxations I just described, the naive relaxation and the perspective reformulation. And for a special set of functions, so for power functions, as it turns out, there is a whole family of natural relaxations between that naive relaxation and the perspective relaxation. And in this paper, we compute the volume of those and compare them and do some computational experiments. But today I want to more talk about this paper here. And here we're going to think about a third way of finding a relaxation for that disjunctive set. So the problem we talked about when we take the perspective reformulation is after doing that, we end up with these conic constraints. Now, instead of taking the perspective formulation of this original function f, what about if we first took a piecewise linear under-estimator of that function f, and then took the perspective reformulation of that piecewise linear under-estimator? Now, when we're taking a perspective reformulation of this kind of linear being, we don't end up with a conic program. We end up with something simpler. So here we're going to find out how that relaxation compares to the naive relaxation and compute some volumes to see if this might be a good thing. Okay. So how are we going to find our piecewise linear under-estimator? Well, I've got my convex function f, and I'm interested in it on this interval between L and U. So what I'm going to do is pick n linearization points, or in fact, n minus 1 with our notation, n minus 1 linearization points between L and U. Each of these points are in the domain of f, and I'm going to assume that my f is differentiable at each of these points. So what I can do is I can draw the tangent line. So I have these n minus 1 tangent lines, t0 to tn minus 1. And for each adjacent tangent line, I can compute the intersection point. So that intersection point is this here. The x value is this tau I, which I can actually compute analytically. But I think it's much easier to see what we're doing in a picture. So I have these linearization points, psi 1 to psi n minus 1. At each linearization point, I draw a tangent. So here I have my tangent T1, and then I define my points. So these P's are what were my taus in the previous slide, as the intersection of adjacent tangent points. And in particular, I define that first intersection point to be at L and the last intersection point to be at U. So I now have this piecewise linear function. I'm going to call it G, and I'm going to define this function as the function that connects these points. So my piecewise linear function G is the function that connects P0, P1, all the way up to Pn, Pn plus 1. And it's pretty clear to see that this is a convex under-estimator of f. And in fact, at these linearization points, it's in fact equal to f. And in the rest of the talk, when I talk about a G, my function G is always defined from my original function f and by this vector of linearization points. So we've got some quite complex notation up here. It needs to be that complex for the paper, but for us, not so much. So what this object is I start with my function f and my vector of linearization points. I find my piecewise linear convex under-estimated G, and then I take the perspective reformulation of that G, and I end up with this object. Now, the volume of this object, it turns out we can compute by this simple determinant computation. So the way to see this is that this object is in fact just a pyramid. The apex of that pyramid is that origin point. The base of that pyramid is essentially the slice, so the piece we have here that now is in fact polyhedral because we did the piecewise linear under-estimator, so it's the yellow part and the blue part. So I have a base, I have an apex, I just have this pyramid, and I can easily compute the volume. All right, so that's a little bit on a general F. The question is, what more can I say if I look at a specific F or a specific family of F? So let's now focus a little bit on power functions. And in particular, first off, I'm going to look at what happens when we just have this simple quadratic function, so P equals 2. So here, my F function is just a simple quadratic, x squared. I am going to have a vector of linearization points. I'm going to take piecewise linear under-estimator and do the perspective reformulation and find the volume. My question is, which linearization point should I pick to get the smallest volume? And as it turns out, what I want to do is space those linearization points equally. So if I have a quadratic, the way to minimize the volume is to have equally spaced linearization points. And the minimum volume is in fact given by this quantity here, where n is the number of linearization points. So we can see that if we let n go to infinity, we're actually going to recover the volume of the perspective relaxation for the quadratic function without first taking the piecewise linear under-estimator. So that tells us that the volume of that is simply 1/18 of u minus L cubed. now this brings up another question. So I have the volume of my perspective reformulation. If I'd done that directly, I have the volume of what happens when I take a piecewise linear under-estimator and then do the perspective reformulation. And now the question is, well, if I just did the naive relaxation, how does that compare to doing this piecewise linear thing? And in fact, how many linearization points do I need to have to make sure I do at least as well as the naive relaxation? And as it turns out, the answer is just one. So you use the L, you use the U, you just have one linearization point, and you're guaranteed to always do at least as well as you would with the naive relaxation. Which is good news, right? Because remember, doing it this way, doing this piecewise linear stuff first, and then doing perspective reformulation, you don't end up with these conic inequalities. All right. So we said that for p equals 2, this even spacing of these linearization points is optimal. So what happens when p is not equal to 2? Well, unfortunately, we can't get closed form expressions, at least yet. It seems to be out of reach to get closed form expressions for where those linearization points can be. However, we can say something. So if I have a fixed L and a fixed U, and I have this vector of linearization points that minimize my volume, then it turns out that in each component of that vector is increasing in P. So I think this is much more intuitive to see in the picture. So here my L is 0, my U is 1. And I have 4, N is 5, so I have 4 linearization points. The bottom blue line represents the first linearization point, etc. The x-axis is P, the y-axis is the optimal value for this linearization. So if I look at P equals 2 and kind of go up, I can see that the optimal value for the first linearization point is 0.2, second one is 0.4, third is 0.6, fourth is 0.8. And this is exactly what I would expect, right? Because that's equally spaced, and I said equally spaced was optimal. Now, when P is less than 2, strictly greater than 1, it's optimal now to be shifted towards the left end of the interval, for all these points to be shifted towards the left end. When P is greater than 2, you can see the opposite happens. It's optimal for those linearization points to be shifted towards the right of the interval, to be shifted towards the upper end. And this is what this theorem is telling us. All right, so what did we say? Well, we said that a closed form for locating even one non-boundary linearization point really seems to be out of reach for P not equal to 2. And a big reason for this is the volume function is in fact not even generally convex in just one linearization point. We can establish that any stationary point is a strict local minimizer, and we can also establish when P is between 1 and 2 that the volume function is indeed convex. For P strictly greater than 2, we can simplify the gradient condition, and we can show that the volume function does have a unique stationary point, but finding a closed form for exactly where they are does seem to be out of reach. So now just thinking about one linearization point, if P is between 1 and 2, then this volume function is convex. If it's greater than 2, then it's quasi-convex, which tells us there will be a unique minimizer. And even though one linearization point may at first glance not seem that interesting, it can actually be useful because we can use some, we would first split an interval by using our one linearization point, and then we could do some kind of greedy idea to then split both halves to find the best linearization point between those. So it could be useful to know. So like I said, it's not generally convex, but has a unique minimizer. And the way we see this is by looking at a related strictly log concave function, which is given here. So by looking at that and doing some more analysis, which Luze spent a lot of time on, even though we can't find closed form expressions for the optimal placement of that one linearization point, we can find bounds. Now, there's a lot more details in the paper and a lot more analysis on how good these bounds actually are. But the thing I just want to point out here, as I'm very close to the end of time, is as you would expect when P is between 1 and 2, the optimal placement for this one linearization point is to the left of the midpoint. When P is greater than 2, it's to the right of the midpoint. All right, so what did we look at today? Well, we looked at the naive relaxation, we looked at the perspective relaxation, and we looked at what happens when you first take a piecewise linear under-estimator and then take the perspective relaxation. In the paper, we actually look at some different scenarios. So here you'll remember we have this assumption that f of 0 is equal to 0. It might be that that's in fact not the case, that our function, our cost function, is defined piecewise. So it's defined to be f of x equals to 0, and then it's defined as some convex piece on L and U. Well, in this case, we can linearly extend the function to 0 and perform the same, do a piecewise linear and look at these relaxations, and the paper goes into more details. So I am out of time. Thank you so much for listening. Here are the references again if you're interested. Yeah, and I look forward to seeing you at the virtual workshop.